So welcome to day 6 of our lecture on machine learning project. So those of you in class, you're welcome, and those of you watching on YouTube, you're welcome. Today we're going to be looking at explainable AI with SHAP, unlocking insights through SHAP. Alright, so we're going to see how using SHAP to unlock the power of explainability. Key points, the thing we're going to be looking at today, we're going to be looking at the use of SHAP. SHAP is a short form for sharply additive explanations, which is used for model interpretability. 2, we're going to identify top drivers of predictions using global and local explanations. Also, we're going to apply SHAP on the previously trained SGP model from day 5. And then also we're going to use SHAP tools such as Beeswax, bar plot, and dependence plot. All right, so let's look at the key learning objectives. 1, by the end of this lecture, you should be able to define interpretability, feature attribution, global versus local explanation. Secondly, you should be able to compute SHAP values for tree-based models, as well as generate and interpret Beeswax, bar plot, and scatter plot. You should be able to use SHAP by the end of this lecture to identify energy consumption drivers. And finally, recognize SHAP's limitation in practice. All right, so let's talk about the importance of explainability. Building stakeholders' trust and mitigate regulatory risks. Like the name implies, explainability simply means to give more insight, provide more information into models prediction. For example, evaluation graphs are not sufficient enough to provide explanation or insight into how the model comes to a conclusion in its prediction process. Now, it is important that we provide some form of guidelines, some form of insight and explanation as to how the model came to a conclusion or came to its decision process. Also, I can give several examples on how important it is for explainability in terms of building trust and confidence in stakeholders. Now, this provides and also shows interactions between features and also gives an insight into which particular features drives prediction. SHAP gives us, or explainability gives us, a clearer picture, a view as to which features influences prediction. So this is how important explainability is in machine learning. Why explainability matters? 1, to build stakeholders' trust. E.g., for example, utility bill. It avoids regulatory risk, e.g. the GDPR's right to explanation. It supports debugging and feature leakage detection. For example, a demand forecast fails due to real-time data unavailability. So SHAP can reduce hidden resilience. Right. So now understanding SHAP in terms of feature attribution simplified. And SHAP utilizes sharply values for accurate feature attribution in prediction. SHAP in a nutshell. Now, if you look at the formula for SHAP, now it gives a prediction which is equal to the baseline plus the sum of all feature attributions. So what this formula explains is that SHAP works based on the contributions of features to model predictions. Now, it predicts based on attributing contribution to each features. So this is how SHAP works. SHAP tries to explain the predictions that is as a result of the attributing contributions of each feature. So it tells us what is the impact of each features to the contribution. What features contribute more and what features contribute least. Meaning that there are some features that drives prediction positively, and there are features that drive prediction negatively. Meaning that some features contribute or increases prediction, while some features decreases prediction. So we're going to see all of this impact. We're going to see features that are not relevant to the prediction process of the model. So this is what SHAP tries to review. Reviews all of this attributing contribution of each feature to the model prediction. All right, so looking at loading data and computing SHAP. Now there are two important lines of code when implementing SHAP. Now we have the explainer, which is the variable that stores or that keeps or stores the SHAP tree explainer function. Now what happened is this. We have the tree explainer, which is a method from SHAP that is used on tree-like models. So what it does is this. It takes the model, the pre-trained model, and then returns that as it returns that function and then stores that into the variable explainer, and then we compute the SHAP values by taking the explainer and then running them on the samples. Now we use sgboost plus the tree explainer for fast computation. We sample 10 rows for fast computation and performance. So the samples are nothing but your data set, but they are nothing but the features coming from the data set. So when we talk about SHAP, we must consider two important factors. One, the pre-trained model. So you must have trained your model and save the weight, save the model that has been trained on the data set. Now you also need the data set, meaning you also need the features of the data set. Now, term of rule, you must ensure that the features you have in your data set must be exactly the same features that is contained in the model that has been saved, meaning the model that has been previously trained using the same data with the same features, right? It must match, it must correlate, or else there will be no way for SHAP to compute its values. So these criteria must be met. One, the saved model, the model that has been trained using the same data set and features must be the same, must match and correspond to the data set samples in which you want to compute the SHAP values. Now, understanding SHAP visualization. Now, let's take the first plot, which is the bees-worm plot, which is known as global feature. All right. So we talked about global features and we talk about local features. So the bees-worm plot is a global feature. So let's look at it. So the bees-worm plot shows feature importance and distribution of SHAP values. Now we have one global snapshot. Now each dot is one row of the data. So each of these dots you find on this plot represents a single observation or record in the data set. So when we talk about the row, we're talking about the observation, the record. It means, for example, one entry. A single entry means the row. So one dot represents a single entry of the data. Then we have the horizontal spread. The horizontal spread, this tells us the impact size. All right, so we're looking at the impact size. When we look at the horizontal spread, we're looking at the impact size, where we have a vertical line starting from 0 up. All right, so the right-hand side rises prediction. Now you have the color. which starts from purple and then spread out to all red. Now we can see that that part to the right raises prediction. It means it affects prediction. It increases the prediction in that direction. All right, while the left-hand side lowers prediction. So it tells us the impact of these futures, okay, towards the prediction. So the right-hand side has positive impact. It means it increases the prediction, while the left-hand side decreases the prediction. It has low impact or negative impact. Now we have the color. We have the red and the blue. All right, so the blue signifies low and the red signifies high. So we could see that the red part of it that spreads to the right hand side has high impact. So the feature that contributes highly to the prediction are apparent power and global intensity. We could see how much they contribute, the positive impact they contribute to increase prediction. Now let's look at the bar plot. Right, so the bar plot is ranked mean of the SHAP. So it takes the mean of the SHAP. Bar plot provides clear comparison of future contribution to model prediction. So let's see how these futures contribute. Now we have the mean of the SHAP ranks overall importance. Right, so for this we look at the mean value. Now we look at the fast top 10 drivers. Okay, view of executive, and then good starting points before deeper dives. Now we can see from the bar plot, we could see the two most important features, or we can say the three most important features that contribute positively. We could see that their values are, you have the apparent power, which is 0.63, global intensity, which is 0.19, and then you have the global reactive power, which is 0.1. So if you put that together, you have approximately about 0.8 to 0.9, okay, which is almost close to 1. So you could see that these three features, they contribute positively, okay, to the prediction, to the increases prediction, while others you can see ranges at 0, 0, 0, 0, 0. It means their impact are not significantly, or they are not significant. The impact of other features such as submetering 3, voltage, submetering 1 and 2, hours, and then other features, they do not have as much impact, or they do not have any impact to the prediction. All right, so let's look at the waterfall plot, which is called the single prediction explanation. All right, so the waterfall plot decompose an individual prediction into contribution from each feature. Now we could see that the bars, the bar shows how each feature pushes the prediction from the base value towards the final output. So we could see from the bar, it starts from the point and then it pushes outward. Now it explains why a specific prediction was made, and then ideal for auditing model decisions at the individual case level. Very useful in regulating settings such as healthcare. So we could see how it pushes forward. We could tell apparent power pushes forward. We could tell that global intensity pushes forward. We could see if we put that together, we have a very huge and great impact on the model prediction. So this is a very nice plot that shows that the global reactive power has negative impact. Okay, because you could see the value negative, and then voltage has negative impact as well. Right, we could see that submetering 3 has some form of positive impact as well, and then hours underscore cosine has no impact or whatsoever on it. All right, so we could see this could tell us the impact of how this model contributes to the prediction. We have the dependence plot, which we call the feature interaction. So this tells us how each features interact. So this tells us interaction of two features together. All right, so this tells us how the sharp values of the feature changes with each value. We could see that while also visualizing interaction effects. So these are interaction between a feature called submetering and r_cosine. All right, so number one, we could see that the x-axis, the value of the selected feature. So we could see the values of the selected feature on the x-axis, the y-axis, which is the sharp value, okay, which is the impact on the model. So we could tell it starts from minus 0.1 and then it goes up to plus 0.02. So it starts from 0.01 and then up to positive 0.02. Right, so we can see the column interaction features where it's auto selected by SHAP if we do not specify. So this is auto selected. We have the blue and the red. So this helps identify non-linear effect and potential interaction between features. This is actually great for understanding marginal effect of features across the dataset. So this could tell us, now we can see it starts from 0 on the bar and then it goes up to 17.5. Now, where you have blue, it means the impact or the interaction between such features is very low. Now we can see across this, we could see the interaction between the two features. This tells us that the interactions are negative. All right, so there are not much interaction between our course and submetering. The interaction are not too, the impact of the interaction are not too great. They're not too great because most of them shows that the interaction between these two features are not too good, not too great. So there are fewer interaction between these two features. Also, this is also simplot like the previous one. All right, so let's look at the real world case study. Sharp insights for municipal utility yield significant cost savings. So a use case is that a municipal utility introduces dynamic pricing. Now, insight from SHAP. SHAP could tell us power cost and voltage drive and how voltage drive peak loads at 6 p.m. Then look at action we can take is to shift tariff. Okay, we could save $120,000 per year with 3% peak savings. All right, so this is an insight from SHAP, and then SHAP, with the help of this insight, we can take some reasonable actions to help us save costs. Okay, now let's look at SHAP best practices. Concerns of SHAP is that it's highly computational. It means the computational cost is very high. How do we mitigate it? We use sampling or tree SHAP. Right, so tree SHAP is efficient and fast. Feature correlation. In order for we to correlate to see how two features correlate, we use SHAP interaction values. All right, to check that. Then we can see that through dependence plot. And then we have model support. We can use tree SHAP for trees. We can also use kernel SHAP for others. Other models that are not tree-like base. They don't use the concept of decision tree or random forest. And then during the lab section, we're going to go through all of this. We're going to see how to compute SHAP values using the data set, the energy data set. We're going to generate visual plot for result, reflect on the insight and gain. We're going to see interaction with pairs for discussion. We're going to compare SHAP result with traditional method. Document the findings for future reference, explore additional resources for deeper understanding, as well as share results with class for feedback. All right, so SHAP bridges accuracy and trust. So SHAP allows us to connect accuracy and trust. So SHAP provides these two elements. Not only does it bridges trust and accuracy, it also gives the confidence that we need to trust our prediction. So by translating feature importance into visual human understanding insight, SHAP empowers analysts, policymakers, and engineers. All right, so at this point, I want to congratulate you for coming this far. In our next video, we're going to be carrying out the practical coding to illustrate and implement all that which we have said today. So all right then, enjoy this video. Bye.